Hello, hello? Ah, okay. Okay, welcome everybody. I have been asked to give this talk in English, so I'm going to speak in English in case someone is not very familiar. Everything is written on the slide, so you can follow this talk even without being very fluent in English. So my name is Raúl Rojas. I'm from the Free University of Berlin. It's free not because you don't pay anything, but because it was founded after the war in the western part of the city. What you see here is our library, and these are our robots. And this was a picture that was taken, which was taken some years ago to publicize the fact that we have been building these robots for several years. So I always say that when we build robots, we are trying to advance the field of artificial intelligence. And artificial intelligence has been concerned with thinking, with rule-based reasoning. But in the last years, many more persons have started working about these kind of things, about subconscious processing that you can do without thinking. So when you recognize a face of someone, you don't have to think about it. When you recognize a speech, you don't have to think about it. It happens in just a few milliseconds. And the most difficult problems for a computer are those problems in which a human does not have to think. If you have to think, it's easier for the computer. If you have to apply rules, like for example in chess, then it's easier to process that with a computer. But if you don't have to think to do it, then it's much more difficult. And there is a new paradigm in artificial intelligence, which is called embodied intelligence. And the idea is that you don't just try to program artificial intelligence in the computer. You try to give the computer a body. So you have to put the computer into the world so that the computer can learn from experience, so that you don't have to program everything, put all the rules in the system, so that the system extracts its own rules from what this system learns about the world. And that means that intelligence needs a body. This is called embodied intelligence in AI. You have to process computer vision in real time once the computer has a body, once the computer has to move around, so you don't have infinite time to process the signals. You have to worry about energy management, so you have to think about the batteries and how much energy is the robot consuming, and when are the batteries going to die. You have to worry about local control. That means what's around the robot, how can I move my robot in a way that it doesn't collide with other objects in the environment. Then you have to worry about communication, because usually you don't want to work with a single robot, you want to work with teams of robots. And the question is how to provide communication in such a way that you get also coordination and team behavior, so that robots are not just acting for themselves, they are acting for the team. And adaptation and learning is something which is very important. I'm going to show you some examples of this, of the kind of learning problems that we have been working on at the university. Robotic soccer is a new AI benchmark. That means it's something that has been just started a few years ago. It was started in 1997, parallel to the International Joint Conference on Artificial Intelligence. And classically, it has been played in 5 leagues. So the idea is that if you are good at building robots, if you think that you have solved some important problems in computer vision, then you can go there and test your algorithms. You can go and try your system and see how good is your system compared to other systems. There is a simulation league where the robots are just simulated virtually on the computer. There is a small size league where the robots are 18 centimeters in diameter. There is a mid-size league where the robots are 50 centimeters in diameter, so much a little bigger than the small-size league. There is the legged league, which is actually the league where Sony robots play. The dogs that Sony sells are used for this league. And there is a new humanoid league where eventually, which is eventually going to absorb all of these leagues. So the idea is that you make the problem more complicated, more difficult from year to year. For example, changing the rules and trying to go from these leagues to this final league in which humanoid robots are going to be playing maybe also against humans at some point. So this is the great vision. reality right now is that the most important leagues are the leagues using robots on wheels. And this is one view of the small size field. It's a 4x by 5 meters field. Usually 5 robots play against 5 robots. So you see here, this is one picture of the final at this year's World Championship in Lisbon. And you see here one of the robots. The only rule is your robot has to be 18 centimeters in diameter and 15 centimeters high. So other than that, you can put anything you want to put into your robot. So if you can put more wheels, you put 4 wheels like we did this year. We have 2 shooting devices. One shooting device is inside the robot to kick the ball flat. And there is another shooting device here, a solenoid, which kicks the ball from the top so that the ball flies in a parabolic flight to the other side of the field. So you put as much electronics as you can put, a communication device, and usually the robots in this league are between 1.5 and 2.5 kilograms in weight. So I'm going to show you one video clip of how the robots play. So it's a very fast sequence. You have to look at the robot on this side. It's going to receive a pass. This robot is going to receive a pass, and then it kicks, and the ball is inside. So it's very fast. Before we had this kind of game, you could play with a joystick against the robots. So you could just control one of the robots and be one of the players. Now the robots are so fast that a human cannot cope with the speed of the robots. I'm going to show you this sequence again so that you can see how fast the game is. So the robot goes for the ball at the corner and then gives a pass, and the robot makes the goal. This is another clip also from the final at the World Championship. Here you are going to see how hard the robots kick. So the kick is going to come from the middle of the field. So the ball is somewhere here. The robots this robot intercepts the ball, and then it makes the score from the middle of the field. So I hope you were able to see that. Otherwise, I can replay that for you, and then you can see again that. That's actually very difficult to see the ball with the camera above the field, because the ball is rolling at about 12 meters per second. So that's the kick, and that's the goal. This is the other league in which we have been working. This is the so-called mid-size league. The robots are bigger, as you can see here. This is our robot. It's the field is much larger. It's 12 by 8 meters in length, so it's almost 100 square meters. And here in this league, 4 robots play against 4 other robots. You can see that also the size of the goal and the size of the regions of the field are much larger. And in this case, the robots have a laptop, so they are controlled by their own computer. They have a laptop or even a desktop. If you can put a desktop in your robot, like for example these guys, they put a desktop in the robot and you can play with that. This is a sequence also from the World Championship this year at Lisbon in June, and you're going to see our robot handling the ball, going forward, and then kicking using the kicking device inside the robot. So and that's the kick, and the goalie has no chance. This is another clip also from the World Championship, where you see the goalie reacting actually very, very well. And then the ball is here, and then the referee has to stop the game to reposition the ball, because there's no way to score when the goalie is just pressing the ball against the goal bar. So that's the only situation in which a human has to intervene to take care of the game. Other than that, the robots are on their own. They are automatically programmed. They play by themselves. And the only thing you can do when the game starts is just look at your robots and see if the things that you program and what you were working on for 1 year works properly. Okay, so let me explain how these robots are built. So these robots start as a software project, actually. So the robots are designed on a computer. And what you see here is the design made by one of our students before the robots were actually built. So we use a CAD program. And then using the program, we just put the wheels and the motors and all the components that we want to build. And when we have the design, we can, for example, look at the kicking device. If the kicking device is properly adjusted, when we have everything, we can send the parts with an email to the manufacturer. So there are many manufacturers of these kind of parts. You can send to them the files, and then you get your parts after 3 days, and you can build your robot. So the only thing is, if you made, of course, if you made an error in the software design, then you will have to go through several iterations until you get your robot. This is an example of the design of the robot in the computer. So these are the motors and the wheels that we use and the kicking device. Everything seen from below. And this is the actual robot which was built. You can see there are some small differences because we changed several parts. But there is a very good correspondence between what we wanted to build and what we actually built at the end. So a robot begins always as a software project where you put your parts together and then you send the robot to be produced. Our robots use omnidirectional control. That means that we use this kind of wheels. We introduced these wheels in 2002 at the World Championship, and now all teams in the small size league are using them. So it's a principal wheel. And then passive wheels on the periphery, so that when you are driving your robot using, for example, 4 wheels, the force produced by each wheel can be added together, and the resultant force gives you the direction in which the robot is going to travel. So that means that, for example, if the force is through this wheel, then this wheel just slides passively on the floor because you have these small wheels that let the robot just slip on the floor. So you can go in any direction without turning the robot. So you can go straight to any other point on the field, and you save a lot of time because you don't have to turn the robot around. These are our mid-size robots. So you see they are like the big brothers of the smaller robots. They also have 4 wheels, same design, omnidirectional wheels, also a kicking device, but now we have a laptop on top of the robot. The robots have their own computer vision, so they have a video camera. So here you see the video camera. The video camera is pointing towards the roof. So it's looking actually on a mirror. And the mirror looks like a cone. So it's a conic mirror. It's not exactly a cone, but it's like a conic mirror. And by looking with a video camera on this conic mirror, and you get a perspective of the whole field. You get a 360-degree view of the field. And using this view, you have to control your robots to make them move around. The robots begin also as a software project, so you can design your robot using the CID program. As here you see one of our first iterations to build a robot with a kicking device inside, which is a solenoid, and then the laptop here. There is also a controller, additional electronics for controlling the wheels and bringing the robot to speed, and everything is being managed by the laptop on top. We have been also building other kinds of robots. I'm not going to show all the robots that we have been building at the university, but this is one of our newest robots in which we have put something like 6 legs. But the interesting thing about these 6 legs is that they rotate around an axis, so that when the robot moves, you only have to be careful that at least 3 of the legs are on the floor, and then the robot can go in any direction. It's flexible. Has 2 joints, so that the robot can go through stairs. So it can go up to the next floor and can come down and can go over rough terrain. So it's another kind of robot that we have been also building. Okay, so let me explain you first about the vision problem. So you have to solve the global vision problem or local vision problem in real time. So that means that you are receiving from the video camera many frames per second, and you don't have infinite time to process them. So in the case of the small size league, we have the robots on the floor. Every team has a camera. The camera is looking on the robots, and the frames being transported from the camera to the computer are analyzed, and when you analyze the frames, then you know where your robots are. And when you know where your robots are, you can send them commands using a wireless link. So the robots have a wireless device, and they receive the commands where they have to go, and the microelectronics on the robot only implements those commands. The robots are colored in order to identify them. There is always a blue team and a yellow team. So this is for example, the blue team. The team color is in the middle. And the other colors, you can use additional colors, are used to identify the robot, to know that this is robot number 1 or robot number 2. So you can distribute the colors the way you want around the robot. And by using certain combinations, then you know where is your robot and which number of robot is that. And the ball is also colored, it's orange, and you cannot use that color on your robots. The first problem that you have to solve when you want to work with global vision is to know what you are looking on the field. And usually you have two problems. You have the problem of the radial distortion, so the world looks round with the camera, and you also have the problem of the projective distortion introduced by not having the camera exactly in the middle and not having the camera exactly oriented vertically. So the field could look like this. Actually, the field looks like this. So it looks like straight lines are not straight, they are round. And rectangles are not rectangles. For example, this side is a little shorter than this side when you make the correction. So the first thing we do is we process the image. We identify the white regions in the image. That means the lines. And using the white regions in the image, knowing that these white points correspond to a line, we compute a transformation in order to make these lines straight. So we compute a radial distortion to make straight lines straight again. And once we have the straight lines, we compute the projective transformation so that we transform imperfect rectangles into perfect rectangles. Using that, you even get the height of the camera. So this is the first step. And now, when we start our robots, we can actually put the camera, and in 1 or 2 seconds, we have all the transformations that we need, and we can compute the positions of the robots. So this is called auto-calibration for video cameras. The second problem that is important is the difference in colors. So color is a subjective impression of the brain. Color is not something totally objective. So you can have a certain color if you're looking with daylight. So daylight has a certain spectrum. So it's a mixture of light of different wavelengths. And this is the spectrum of sunlight. But lamps have a different spectrum. Like, for example, this is a fluorescent lamp, and this is a tungsten lamp. So you see that the tungsten lamp is always has a little more yellow. That's why using digital cameras, your pictures are always a little yellow, because the camera is right, your eyes are wrong. The light is yellow, so that's the correct thing to do. But you don't want the correct thing from the camera, you want the incorrect thing. That means what you see, what you actually process with your brain. And this kind of processing, this is called color constancy in humans. It's the capability that we have to eliminate the spectrum of lighting from the image. So we just compute it away so that colors look the same way under different kind of lighting. So a video camera is not provided with that capability. A computer also is not provided with that capability. And what we do is that we use adaptive color maps. So that means that when we look for the ball, or when we look for colored objects on the field, we store the parameters of the color. The colors are stored in different formats using a set of numbers. But when we find, for example, the ball, we store the parameters here, where the position where we found the ball. If we find the ball here, we store the parameters here. If we find the ball here, we store the parameters here. And you can see that the color looks different. So actually, this is a region of the field where there is more light, so that the orange looks a little like yellow. But you can identify the color because we have a grid on the field. And it's an adaptive grid. Every time the robots are running around, every time the ball is moving, we are updating this grid. We are updating the parameters so that using this grid, you can actually turn down the light slowly. And if the robots are moving and everything is moving, then the grids update and you can continue processing the colors. You can even change from daylight to tungsten lamps to artificial light slowly. And if the robots are moving, then the grid is adapted and you don't have any problem in your vision processing. This is like a simulation of what humans do. This is a little like color constancy for humans, but using not the parallel processing that we have in the brain for this, but using a grid which simulates this color constancy. Another very important thing that we use is we try to process as many frames as possible from the video camera. We work with 50 frames per second. And when we are tracking objects, we don't look for this object in the whole image. So we don't look around, let's say that you have a picture with 500,000 pixels. We don't look at the 500,000 pixels for the ball. We have an estimation, we have a forecast of the position and movement of the ball, so that next time that we look for the ball, we look in a region of the field, in a small frame. If the ball is there, we are satisfied and we continue processing. So we do our next forecast for the position of the ball. We look only at these pixels, not at the 500,000 pixels that we actually have. And if the ball is not there, is not located in this region of the field, then we just increase the size of the region. We duplicate the side length of the frame, and then we look again, and if the ball is here, then we are satisfied. If the ball is not here, then we duplicate again, and then again and again until we cover the whole field. So we can finish looking in all the pixels, but we try to look in an intelligent way by going from our forecast radially around the field. And if the next time when we have this larger frame, we find the ball inside this larger frame, then we reduce the size of the frame. So we go from small frames to larger frames, and then from larger frames to smaller frames, according to if we find the ball or if we don't find the ball into these frames. So it's also an adaptive region that we use for looking for the ball. When we are looking for the robots also, there is a very important problem, and the problem is there is a certain delay when you are looking at your colors. There is a certain delay between what you see at a certain moment of time, t, and the position of the robot, because at this point the camera has shot a frame, and this frame has not arrived to the computer. So we are waiting for the frame to arrive to the computer, and when the frame finally arrives to the computer and we are able to process that frame, we have data from the past, we have the past frames, but the robot has moved. So we need data about the future. So what happened to the robot during the time we were waiting for the robot, for this data to arrive, and during the time we were processing the data. So there are two parts for this delay. There is a vision delay. That's the time it takes for the video frames to enter the computer and be processed. And there is a communication delay. That's the time it takes for the commands to go from the computer to the robot. So that you have to make a forecast. You have to use this data. You have to use the past. Let me see. You have to use the past, but you have to predict the future so that you can do intelligent control. So what we do is that we use a predictor. So we use, in this case, the predictor could be a neural network or could be just a linear function. It's just a linear combination of these inputs. We use the positions of the robot in the past. So these are the last 4 frames that we saw. And we use the commands that we send to the robot. If we send commands, we expect the robot to move in a certain direction. And we know which commands we send for the velocity in the x direction, the velocity in the y direction, and the angular velocity for the robot to turn around. And we look at the 4 last commands that we send during the 4 last frames. So using this information, the 4 last positions, the 4 last commands, we make a prediction. And the prediction tells us where we think that the robot will be in the future. Not really where the robot is now, but where the robot will be in the future when the command arrives that we want to give to the robot. This is very important because the robots are very fast, as I told you. And the delay is around 100 milliseconds. The robots can roll at between 2 and 3 meters per second. And 2 and 3 meters per second in 100 milliseconds is from 4 to 6 or 7 centimeters. So that's the difference between bumping into another robot or not bumping into the robot. That's the difference between stopping at the right time and not stopping at the right time. And that's very important because there are yellow cards and there are red cards, and if you bump into a robot and send the robot out of the field, then you get a red card and you have one robot less in your team. So the predictor helps us to find a bridge between the information from the past that we have and the information about the future that we need to have a good control of the robots. And this is what we get from the predictor. So this is actually a robot moving in a sharp curve. What you see here, these little blue fingers, this is the prediction that we do at every frame. So we predict the next 4 frames, and you can see that our prediction is a little off. There is a small error, especially here at the sharp curve, but there is a smaller error here when the robot is going straight. And the error is not so big that we cannot control the robot. So what you see here is an actual curve from a robot that has learned to bridge the difference between the past and the future. And if you don't use this kind of predictive movement for the robots, then the robots tend to oscillate. So you get robots that oscillate, don't drive very well, and then you have to reduce the speed of the robots. But we want to drive at the fastest possible speed, and that's why this kind of prediction is then very good. Okay, so these are 3 problems for the small size robots. One problem was the lightning, how to adapt to lightning. The other problem was how to do the tracking of the robots on the field. And the last problem was how to predict the future movement of the robots. Now let me talk about the bigger robots. These bigger robots started being small. These were our first robots with their own video camera. And you can see here, what we have here is a small video camera which was actually sending the frames to an off-the-field computer. And what we used at the beginning for our mirror was not a conic mirror, was just a mirror from a lamp. A mirror from a lamp is good enough to get omnidirectional vision. And then you just spend €1 and you get a very good mirror. The kind of images that you get from these mirrors are like this. So this is a spherical mirror, this is a parabolic mirror. There are differences between the mapping of the surface of the field between these 2 kinds of mirrors. But something which is very important is the direction is always right. So if there is an object here, the direction in which your robot is looking at this object is always right. The distances are compressed, so they are not the real distances, but the angle is the correct one. And you can compute using this correct angle. So this is an actual picture using our mirror from the field. So here you see the robot located between the middle line and the goal line, and here you see the robot located at the corner. So this is the kind of perspective that we get. Then we process the image. We try to find the transitions between green and white in these pictures. And by finding the transitions, then we know where the white lines are located. We don't know where the robot is, but we know where the white lines are located, like for example here. So this is an example with a smaller field in which you see the rays going straight from the middle of the robot to the outside. Then we locate the transitions between green and white. And using these transitions, we have a cloud of points. So we have many points, which give us an idea of the position of the white lines. And by looking at these white lines, then we just have to adjust this cloud of points to the model of the field. So this is a simplified example in which I'm assuming that the model of the field is 2 rectangles put together. This is the cloud of points which the robot is seeing. The robot is in the middle. So we put the robot at the beginning here in the center. And the cloud of points is not matching the model. So what we do now is that we think that the model is charged with a negative charge. So assume that these points are negatively charged, and assume that the frame is positively charged. So what happens then is that the model attracts the negative charges, the cloud of points, and if you iterate once, then the cloud comes nearer to the model. The robot is displaced to another position. If you iterate again, then the cloud moves closer. And if you iterate several times, then you get the best possible fit There is some error in the vision. That's why here this line is not exactly right. But this is the best possible fit from the cloud of points to the model. And the total displacement gives you the position of the robot on the field. And the total rotation of the robot gives you the orientation of the robot. So it's a very simple algorithm. This is called the expectation maximization algorithm in computer science. It means that you have an expectation of what you think is the right thing, the right correspondence between the cloud of points and the model. And then you make a step in that direction, maximizing your expectation. And the next time you repeat that again and see if your expectation can be again maximized. And if this converges, then you get a solution for your problem. Like in this case, where you have the orientation and position of the robot. This is an actual example from real data from the robot. This is the localization of the white lines that the robot did using the laptop. And then the model is attracting. So the green lines is the attraction on the cloud of points, trying to make this cloud of points fit the model better. And since we are tracking the robot, we are following the robot using 30 frames per second, then it never happens that the robot is too far away from where we expect the robot to be. That means that the cloud of points is not very far away from the model. And the number of iterations that we need is low. But you can even make it faster if you think that the model is just like a field of charged particles, and then you pre-compute the force. You don't have to compute the force for every pixel every time you have a cloud of points. What's the attraction of the model on a pixel, for example, located here? You can pre-compute it at the beginning. You pre-compute the field, and then when the cloud of point arrives, you just have to read off from a matrix. So this is a big matrix with a lot of data. You only need to read from the matrix what's the total force on each point. If you have 100 points, that means that you have to make 100 reads from the matrix, and then you have to add the forces together, and then you get the translation and rotation that you need to fit your robot on the field. Okay? So the next problem is obstacle detection. When you are using this kind of robots, you don't have a camera from the top looking at the robot, so you don't exactly know where are your own robots and where are the robots from your opponent. And what every robot does is that they look around and they identify not only white points, they identify also black points, so black objects on the field. The robots have to be black when they are used. So this robot is identifying these positions on the field, which are black, and then it makes a model. It assumes that there is a certain object, a robot located at this position with a certain spread, with a certain variance, and then puts a circle in the middle. And it says, I assume that there is a robot here with this variance, and I assume that there is a robot here with this variance, and so on. All robots that we are using send their data using a waveland. So actually, our system is a moving network. It's a moving waveland. Every robot is connected with a waveland to an off-the-field computer. So they send the data, and when the data arrives, for example, of two robots, we have one robot here and one robot here, then we combine the information from all the robots. For example, this robot is seeing an object here, and this robot is seeing an object here. So we compute a combined prediction, the best combined prediction that we can have for all the robots. And since our robots are telling us where they are, this robot is telling us, I'm here, and this robot is telling me I'm here, and this robot is telling me I'm here, then I recognize my robots and I recognize the opponents. So this is a 3 against 3 game, where I have recognized, I have identified and found my 3 robots on the field, and I have recognized and identified the other 3 robots on the field. So obstacle fusion is a very important thing. And I can also make a prediction of the movement of the robots, so that next time I look for these objects, I can look in a reduced portion of the field. Okay, so next problem is how do robots work? How do they react to the world? How do they organize as a team? What we use is reactive behavior, so we don't have a plan from the top to the bottom. So we don't let the computer think for many seconds what's the best course of action. So what we do is that we let the robot just react using reflexes. We have sensors for the robots, we have behaviors, and we have actuators. Sensors means that we have the video camera and we have certain parts, certain portions of code, so certain small programs, using this information to find, for example, the ball. So finding the ball with a small portion of code is called a sensor. Finding a robot with a small portion of code is also called a sensor. We can have a sensor for the goalie in the other team. So we can be looking around if the goal is in the box or is not in the box, and then we say this portion of code is a sensor. When sensors have information, they can trigger behaviors. So once we know that something is happening, you can activate code in the robots that tells the robots to do something. Like, for example, kicking. If the ball is in front of you and you are looking to the goal and the goal is not there, just kick. Don't think anything else, just kick. Don't try to analyze the situation. Why the goal is not there, just do the right thing. And there are behaviors which are triggered very fast because you have to have the answer immediately. Like, for example, kicking. But there are other behaviors which are triggered in a slow fashion. That means that, for example, if you decide that your team has to go on the offense or has to go on the defense, you don't decide that every millisecond. You decide that once a second or once every 2 seconds, because once you decide that your robots move forward, you don't want your robots to oscillate, to start moving in one direction and then the other. So there are behaviors which have to be triggered at a low frequency, and there are behaviors which have to be triggered, for example, every frame, every 50th of a second. And actuators means that there are parts on the robot that we activate, so we push a button on the robot, and the robot kicks or the robot moves, and there are also virtual buttons. So when we want the robot to go on the offense, we press the virtual button that says this robot is on the offense, and then this robot keeps being on the offense for several cycles. So what you see here is a cycle in the processing, and we repeat this cycle 50 times a second. So 50 times in every second we are evaluating the sensors, we are evaluating the behaviors that are being triggered, and we are evaluating the actuators, or the actuators are being put to the correct value. So let me show you that with a view of our software. This is the way it looks in our software. This is the actual game. This is the 5 robots being tracked and 5 robots being tracked, and this is a simulation. So we have a simulation that we can use to test the robots. Before we use the robots on the field, before we do anything with the real robots, we first try the code here. If it works fine in the simulation, then we use the real robots. And what you see here are the behaviors of the robot, the reflexes. Some reflexes are going up, and some reflexes are going down. And using a certain combination of reflexes, then you can achieve team play. So the real interesting thing is how to program robots which are not thinking about the team. They are just working to do something by themselves. But anyway, you have something like team behavior. And I'm going to give you an example. Let's say that this robot is going for the ball. So the robot is here, the ball is here, and this robot is located at this position. So we have programmed our robot so that when a robot moves on this side of the field, the other robot just follows the first robot like a reflex. So this robot just tries to keep at the same distance from the middle line as this robot. So when this robot moves forward, this robot moves forward. This robot goes for the ball. So this means that its approach behavior is active. So the robot is moving. This is time. The robot comes to the ball, behind the ball, and then the kicking behavior in this robot is not activated because the angle is too steep, and also because the goalie is here. So there's no way of kicking inside the goal here. But then the passing behavior is activated. So this is the correct situation in which the passing behavior can be activated. The robot kicks the ball in the middle of the field without really knowing if this other robot is here, without calibrating the kick to the position of this robot. But this robot is going to be here because we programmed this robot to follow the other one. So when the ball arrives, the kicking behavior in this robot is activated, goes up, and then the robot finds the ball and kicks the ball inside. So that's a combination of two robots in which each robot is just playing for itself, but then you get combined game. And that's also like in actual soccer. In actual soccer, when you get a pass from the side, many times the players do not look to the other players; they just do it automatically. It's a reflex. It's a reflex that the players have just learned. So let me tell you something about learning. So I think that's the most interesting part, and this is what we have been working on this year, and we are going to show next year also at the World Championship. What we would like to do is to have a coach for the robots. So right now we program everything by hand. So we go and we have very good programmers. They program everything. We would like to have a coach where the coach comes and just draws 4 circles and says, if the enemy is here and if my 2 players are here, give a pass. And then the robots learn from that example. So we just paint an example, and the robots learn from that example and learn to do it. So what we do is that we have several features from the field. So we don't give this drawing to the computer. What we give to the computer is a modified representation of the field. Like using, for example, what's called unpassbar kite. So what kind of is the field open to give a pass? So in this example, the field is open to give a pass. So we give this example and we say this parameter for this field has a very high value. Another parameter which is very important is how much space is there around the robot without an enemy. So for example, this robot has the ball and there is a lot of space here where there is no enemy. So it could be that it's better to drive a little with the ball before giving a pass because there is so much space. So in this case, we compute a variable, a feature of the field, which is called space liberty, so to say. And this feature of the field is passed to a classifier. So we have several features that we compute from the field. And then we have our coach. Our coach is a student who sits there at the computer and puts these enemies here and says, if I have my robot here and my robot here, this robot shouldn't drive. This robot should try to give a pass to this robot. This is a good example of a pass, of what could be done with a pass. And then we enter the many examples. In this case, we have 100 examples that were entered just by drawing on the computer. And then the computer learns. The computer learns to identify positions on the field where it is easy and it is good also to give a pass. For example, there is a player here. This player has the ball. If this player has the ball, then this other player should move here or should move here. So this is just a classification which is being done by a computer, it's a neural network, a classifier, based on these static examples, 100 examples entered by a coach, and the computer has learned from the coach that the good thing to do if you want to give a pass is to give the pass here or to give the pass here. And then my other robot just drives into this portion of the field and tries to get the pass when the pass becomes available. Let me show you, this was not done with that system, but it's a nice example of a reactive pass. So it's very fast. So look at the robot on the other side. And this is the replay with using a slower motion. So and this is exactly like the situation I told you before. This robot here has no idea exactly where this other robot is located, but it gives the pass in the correct direction and the other robot reacts reflexively to the same situation. Here you have another example. This example is of a robot that cannot kick because this robot is on the way, then the robot goes away and then it can kick. So there is no real coordination between the robots. Every robot is playing for itself, but you get coordinated play. And that's the art in this case. And also predicting the future is very important, like you see here. So it's very fast, so I'm going to replay it again. The robot here, the goalie, is trying to predict the future of the ball. It's not just following the ball, it's predicting the future, and by predicting the future, it's able to position itself at the correct position. So just look at the kick. It's going to come. So the kick comes, and the goal is at the correct position when the kick arrives, because the ball is being predicted, so that you don't have to react at the wrong time. Okay, so this is another very interesting part, I think, from our work. And the idea here is that we have taught our robots how to move on the field. So that means that what you see here is a robot trying to move along this path, the blue path, but the robot is not able to follow the blue path. The robot follows actually this green line. That happens because the robot tries to go at the fastest possible speed, and the four wheels are have not exactly the same grip on the carpet, so that when the robots accelerate, then they turn around, depending on which motor is the fastest motor to accelerate. So that means that you get a curve. So the robots, when they start, they don't move exactly in the correct direction. But then we do the following: we let the robots learn how they drive. It's like if you have, for example, a person, and you tell this person, go to the left, and the person goes to the right, and you tell the person again, go to the left, and the person goes to the right. Next time you don't say the person go to the left, you say go to the right, and the person goes to the left. So you learn using the computer and using the vision how the robot really behaves when you send the commands. You don't assume that the robot executes the commands perfectly, and by using this learning, we can do this. So you can drive the robot in the correct way. Even more impressive, I think. Let me show you the other example, and I tell you how we do that. Even more impressive is this example. This is something that happened to us at the World Championship this year. We were driving our robots with 4 motors, but we use the motors at twice the voltage that have been produced for. That means the motors are for 6 volts, and we drive the motors at 12 volts. So that means that we are faster, but it means that we also burn the motors, and we burned a lot of motors during this championship. So when you burn a motor, when you have 4 motors and you burn one, then your robot moves like this. So the robot is trying to go in the straight direction, but it moves like this. And using this kind of learning again, where you don't assume that the robot is going to move in the direction you told it, but you look in which direction the robot moves, and then you make a prediction, then you can make the robot move in the correct direction, more or less, no? Like you see here. So it's even better than the other robot. So the way to do this is just to invert the prediction. And what we do is, I told you before that we have a predictor. We can give the positions, we can give the commands, and then we get the predicted position of the robot. So now you can invert this. You can measure what's the robot really doing, where are you finding the robot, and this is an input to the predictor. And you can ask the predictor, what's the robot really doing in terms of velocity, in X and Y direction, in terms of rotation. So by inverting this function, then you get the correct command that you have to send to the robot if you want the robot to go here. So that's what we did in order to get this kind of behavior. So that means that you have your robots, they are moving around, they have only 4 motors. You burn 1 motor, but the vision recognizes that and adjusts immediately, online. And you can even burn another motor. You can use 2 motors and you can still move. And we have tried even 1 motor. With 1 single motor, you can still move your robot because you can swing the mass of the robot around and then the robot can still move. And this can be done online and can be done by learning. Okay, so just let me finish because I just have a few more minutes. So this is our statistics. I wrote this in German because there is no word in English for Vize-Weltmeister. We have been 3 times runner-up to the World Championship, 1999, 2000, and 2002. We have been 4 times the winner of the European Championship and of the German Open, which is a kind of European championship. And this year we could win the 1st place in the small size league. So we are the champions in this league. And we got the 4th place in the mid-size league. From among a field of competitors of 24 teams from around the world, from many other universities. So let me just show you the work that we are going to do this year also. We are moving our computer vision system to this kind of vehicles. we would like to have an electrical vehicle driving around. And for this, we have designed a new kind of mirror. And this is a simulation of the mirror. So if you're driving, if you're going through the street, then you would like to have a computer that can see the crossings. So what you see here, so I stopped too late. Let me start it again. What you see here is a car going across a street. So that looks like a curve. It's actually a street. And then using this kind of mirror, you can see to the left, you can see to the right, 180 degrees. And to the front, you have the same kind of perspective that you have with a normal camera. So using this, you don't have the impression that you always have with a camera that you cannot see to the sides. So here you can process everything that it's to the sides of the car. Okay, let me skip that because it's not important. So let me just tell you about the people who did all this work. So building these robots is teamwork, and the robots were built by many students working on the small size team, coordinated by Alexander Gloye, who is a PhD student at the Free University. Then we have the mid-size team, also with many students working there, coordinated by Felix von Hundelshausen this year, and where you see the students that were collaborating. This is the people who built parts for the robots from the physics laboratory, and this is the people who built part of the robots from the Max Planck Institute, also collaborating with us here in Berlin. So this is our robots, and this is the championship, and this is the way we went to the city of Paderborn when we went to the German Open. So thank you very much, and maybe you can still ask some questions if the organizers agree. Thank you. So I don't know if, I think we are over the time, so we just stop here. Thank you.